It's a heavy July afternoon in 1954 at Haneda Airport in Tokyo. The air is thick with heat and engine noise when a well-dressed businessman steps up to the immigration counter. He smiles politely, opens his briefcase, and hands over a passport from a country called Taured. The officer frowns. He's checked hundreds of passports, but he has never seen this one before. The stamps look real. The visas line up. The man calmly explains that Taured is a small nation between France and Spain, and that he has traveled through Japan many times for work. Everything about him feels perfectly ordinary until they pull out a world map. "Here," he says, tapping confidently on the spot where Andorra is. "There is no Taured. Not on that map. Not on any map." The more they question him, the more the story holds together and the less sense it makes. Out of options, security escorts him to a hotel room under guard while they figure out what on earth is going on. By morning, the room is empty. No broken locks, no witnesses, no camera footage. The man from a country that doesn't exist has vanished, leaving behind nothing but a story that refuses to die. Maybe it was a hoax, a mix-up, a legend that grew in the telling. But the reason it haunts us is simple. It points to a deeper fear and a deeper hope. Could the universe really allow someone to slip from one place or one time into another? This video won't try to prove whether Taured was real. Instead, we'll use it as a doorway into a bigger question. If the universe truly allows extreme travel to the edge of space, far into the future, or even toward the past, what do we gain? What do we lose? And why is nothing ever free? To talk about someone stepping out of place, out of time, we first have to ask a quieter question. What exactly is this place we think we stand in, and what does it mean for time to pass at all? We grow up with a very simple picture. Space is a giant room with three directions. Time is a single line running through it, ticking the same for everyone. You move around inside the room, and time flows past you like a river you do not control. It feels obvious. It feels built into experience. Relativity takes that comfort away. When you look closely enough, the universe is not a three-dimensional stage with a separate clock nailed to the wall. It is more like a four-dimensional object, a solid structure of space-time. In that structure, every event that ever happens is a point. Your birth is one point. You watching this video is another. Your death is a third. If you could see the universe from the outside, you would not see a movie playing. You would see all frames at once, fused into a single whole. A physicist calls the path that links all the events of your life a worldline. It is a thin thread running through the space-time structure. It starts somewhere in the early 21st century, on a small, rocky planet. It winds forward through school, work, relationships, late nights like this one. Somewhere, it ends. All along that thread are the moments you call now, one after another. From your point of view, you walk along that line. From the point of view of the space-time block, the entire line is already there. A common picture helps. Think of a block of clear jelly. Suspended inside are thin strings, twisted and tangled, each one representing the history of a person, a planet, a photon from a distant star. You can slide a knife through the jelly and take a thin slice. That slice is like a present moment. It cuts across many strings at once, showing where everything is right now. But nothing in the jelly itself says which slice is the real present. You can cut it at a slightly different angle and get a different set of simultaneous points. For someone moving very fast or sitting deep in a gravitational field, their slice of what counts as now, through the block, is tilted compared to yours. This is the strange lesson of relativity. There is no unique global present. There are only different ways of slicing the same four-dimensional structure. This is where extreme travel really lives. It is not just racing across space like a ship on an ocean. It is about how sharply you bend your world line through that structure. If you stay at home, you take a gentle path. Your world line is almost straight. You move mostly in the time direction, barely drifting across the map of space. You age steadily. Your friends' world lines stay parallel to yours. Your sense of now overlaps with theirs most of the time. If you decide to move fast, to accelerate hard, or to fall into a region of strong gravity, you change the geometry. Your world line tilts, curves, dives closer to the edges of what relativity allows. You begin to cut through the block in a different way. Your now no longer matches the now of your family, your city, your planet. From the inside, that feels like time speeding up for others, slowing down for you, or vice versa. From the outside, it is nothing mystical. It is nothing more and nothing less than geometry. The speed of light plays a central role here. In spacetime diagrams, light defines the sharpest angle any causal influence can have. No world line of a massive object can ever tip over that boundary. You can lean closer and closer to that limit, but never cross it. You can think of it as a kind of glass wall in the geometry. You can press against it with more and more energy. And the structure responds by stretching your time rather than letting you break through. That is one of the first prices the universe charges. Push your world line toward that light-like boundary, and it makes your clock slow relative to others. You do not get both high speed and shared time. You have to choose. Gravity adds another twist. A massive object, like a planet or a black hole, is not just sitting in space-time. It reshapes it. Near a massive body, the straight-line paths in the geometry curve inward. Time runs at different rates, at different height. Your world line is pulled into a new shape. Stay close to a massive object, and your thread through the jelly stretches differently. For someone far away, your time appears to crawl. For you, distant events seem to flash by. The same structure, the same physics, different, cut through the block. The unsettling part is what this picture suggests about your life as a whole. If all events are just points in a four-dimensional object, then in some sense, your future self already exists somewhere within that object, just as your childhood self still exists somewhere else. You are simply not there yet, along your own world line. Does that mean your choices are an illusion? That everything is already written? Some physicists and philosophers lean in that direction. Others argue that the block description is compatible with genuine novelty, that the already there language is just a way of talking and not a deep statement about fate. The laws of physics, as we currently write them, do not settle the argument. What they do say, clearly, is that any attempt to create extreme paths through the block comes with constraints that are not negotiable. Try to make a world line that loops back on itself, and you run into closed time-like curves and paradoxes. Try to make a shortcut across the jelly, and you run into wormholes that collapse unless fed exotic forms of energy. Try to push a human body along a path that skims the edge of a black hole, and you run into tidal forces and radiation that care nothing about your plans. At a more modest level, even moderate bending has a human cost. Take a long, high-speed journey, and you return younger than those who stayed. In the block picture, your world line simply covers less proper time between two shared events. In your life, that means missing funerals, birthdays, the slow aging of people you love. The geometry does not register loss. You do. There is also a quieter consequence. If the universe is a structure, not a stage, then distance itself becomes slippery. In ordinary language, we ask how far it is to a star, as though there were a fixed gap you could cross with enough patience. In space-time terms, that gap is part of a four-dimensional web, shaped by expansion, curvature, and motion. Two galaxies that are near at one cosmic time may be forever out of communication at another, not because anything accelerated away inside space, but because new space-time has formed between them. Their world lines drift apart in a way no rocket can undo. Their past light cones overlap. Their future ones do not. From inside your own small segment of world line, all of this is hard to feel. You wake up, You check the time on your phone. You walk down familiar streets. It is natural to treat the universe as a big room in which things move around. But underneath that everyday picture is this more severe one, a four-dimensional structure in which going somewhere means carving out a path between events, and where some paths are allowed only if you are willing to accept what they do to your time, to your body, to your relationships, to causality itself. When we ask how far we can go, we are really asking how much we are prepared to deform our thread through the jelly. Stay gentle, and your Worldline remains close to the quiet bundle of lines that define human life on Earth in this era. Push harder, and you peel away from that bundle, out toward more isolated regions of the block. The laws of physics will let you do that, at least in principle. They will not stop you with a sign that says, "Forbidden." Instead, they reshape the costs. Every serious proposal for extreme travel, from near-light-speed voyages to dives near black holes to speculative wormholes, is really a proposal about geometry, how to tip, stretch, and twist a Worldline inside a structure that never gives you every advantage at once. Energy is one part of the price. Engineering is another. But the deeper cost is always paid in how your path diverges from those of everyone and everything you care about. Once you begin to see the universe this way, as a structure rather than a place, even simple questions about distance and direction sound different. You stop asking where the edge is, and start asking which parts of the space-time web can ever be linked to your own thin line, and which will remain forever out of reach, no matter how clever we become. But a web is hard to feel from the inside. What we feel are steps, roots, and the old question that never quite leaves us alone. If we keep going outward, does the universe ever actually let us arrive? Astronomers tried to answer that long before they had rockets that could do more than skim the edge of our own planet. They did it by turning telescopes toward pieces of sky that seemed completely empty and simply waiting. In the mid-1990s, the Hubble Space Telescope stared, almost obsessively, at a patch of darkness in Ursa Major for more than 100 hours, spread across roughly 10 days of repeated exposures. That patch was about the size of a grain of sand held at arm's length. Inside that grain of sky, the Hubble Deep Field revealed around 3,000 galaxies. Each one of those galaxies contained billions of stars. The part of the universe that looks like nothing to the naked eye is already far beyond anything our bodies will ever cross. That is the first pushback the universe offers. Distance is not rare, it is the default. From those observations and many others, cosmology now estimates that the observable universe has a radius of roughly 46 billion light-years. A light-year is the distance light travels in 1 year of vacuum flight, on the order of 10 trillion kilometers. The edge of the observable universe is tens of billions of those stacked end to end, and that is just the part from which light has had time to reach us since the hot, dense beginning of our cosmos. We have also learned that this enormous region is not static. Space itself is expanding. Distant galaxies are not simply moving through an existing arena the way cars move down a highway. The arena itself is stretching. Beyond a certain distance, that stretch carries galaxies away from us faster than light. Not because any rule is being broken, but because relativity allows space-time to grow without treating that growth as motion. Their light, emitted long ago, is still reaching us now, but any signal we send back will never catch up. So when we ask how far we can go, we are already asking a question with two different layers. How far can we travel through the part of space that is still, in principle, reachable? And how much of the universe lies beyond any possible contact, no matter what engines we someday build? Our practical attempts so far are small threads against that background. The most distant human-made object, as of the mid-2020s, is Voyager 1, a spacecraft launched by NASA in the late 1970s. After gravitational slingshots past Jupiter and Saturn, it has been drifting outward for almost half a century. It is now around 25 billion kilometers from Earth, out in interstellar space, communication delayed by many hours of light travel time. That sounds vast, and in every human sense it is. But compared to the tens of billions of light years that define the observable universe, Voyager's journey is like a single grain of dust drifting a few millimeters across a map of a continent. Even compared to the distance to the nearest stars, Voyager is still close to home. The closest known star system, Alpha Centauri, sits a little over 4 light-years away, with Proxima Centauri as the nearest individual star. At Voyager's current speed, a bit over a dozen kilometers a second, it would need tens of thousands of years to get there, and that is assuming it were aimed in exactly the right direction, which it is not. Because of numbers like these, serious thinking about interstellar travel quickly turned toward designs that are more than just scaled-up chemical rockets. In the 1970s, the British Interplanetary Society carried out a study called Project Daedalus. The team asked whether, using only physics and technology that did not obviously violate known limits, an unmanned probe could reach another star within a human lifetime. Their target was Barnard's star, a small red dwarf roughly 6 light-years away. The design they arrived at was enormous. A multi-stage fusion rocket with a mass of tens of thousands of tons, burning pellets of fuel at a blistering rate to reach a cruising speed of more than 1/10 of light speed and cross the gap in about half a century. Nothing like Daedalus has ever been built. The point of the study was not to draft blueprints for an imminent mission. It was to ask a sharper question. If you take known physics seriously and push engineering to its speculative edge, what does the universe still allow? Decades later, the Breakthrough Starshot initiative posed a different version of the same question. Instead of one massive ship, it imagines a fleet of gram-scale probes attached to thin light sails, driven by the pressure of a vast ground-based laser array. In principle, bathed in that focused light, these tiny craft could be pushed to around 1/5 of the speed of light and reach the Alpha Centauri system in a few decades. The idea draws on real laboratory work on light sails, nanotechnology, and laser optics. But it also lays bare the cost side. A laser system with power measured in tens of gigawatts, exquisite aiming across interstellar distances, and probes tough enough to survive impacts with dust grains at relativistic speeds. Both Daedalus and Starshot live in the same space between dream and constraint. They do not require new laws of physics. They do require us to gather staggering amounts of energy and pour it into a very small path through spacetime without losing control. Even if we imagine that challenge met, the expansion of the universe imposes a quieter boundary. There is a spherical region around us, defined not by walls, but by time. Light emitted today by a very distant galaxy beyond a certain distance will never reach us, because the space between us and that galaxy will have expanded too much in the meantime. Likewise, any signal we send now will never arrive there. That boundary is sometimes called a cosmic event horizon. The important point for our question is this: no matter how clever our propulsion becomes, any ship that respects relativity is limited by the speed of light itself. It can cross only those parts of the cosmos whose world lines still intersect ours in the future. There are regions, already present in today's universe, that are permanently sealed off, not by law, but by geometry. Closer to home, even the reachable distances demand strange sacrifices. Suppose we manage to build a vessel capable of cruising at, say, half the speed of light. To get there, we would need to accelerate for months or years, then decelerate again at the other end, all while protecting a fragile human body from radiation, micrometeoroids, and simple psychological exhaustion. The proper time experienced on board might be less than the time that passes on Earth, thanks to time dilation. An astronaut might live through 10 years of travel while decades have gone by back home. For them, the stars become nearby neighbors. For everyone they left behind, they have become almost a myth, a message that left long ago and has not yet returned. This is part of the universe's answer to how far as well. Distance in space is inseparable from distance in time. Travel far enough and fast enough, and you begin to skip ahead in the shared story of your species. The cost of reaching distant systems is not only measured in joules and engineering challenges. It is measured in birthdays missed, Cultures evolved beyond recognition, languages drifted, histories rewritten without you. There is also the question of what you can bring back. A ship that travels at a significant fraction of light speed through interstellar gas and dust will endure a constant hail of high-energy impacts. Its shielding will erode. Its instruments will fail. Any fragile cargo, whether biological or informational, will be under long-term stress. When we talk about sending humans to the stars, we are really talking about surrounding a small pocket of Earth-like conditions with extraordinary layers of protection and repair, carrying that pocket for years or decades through a deeply hostile medium. On cosmic scales, that effort remains local. In the age of Hubble and the James Webb Space Telescope, our deepest views of the universe still come from telescopes that have not left our own neighborhood. The Hubble Deep Field and its successors gave us a core sample of cosmic history by staring at a fixed patch of sky rather than by going there. Gravitational wave observatories have let us sense black holes colliding in distant galaxies without budging from the surface of our planet. These are forms of travel by attention, where light and ripples in spacetime do the moving and we stay home. You could see that as a kind of surrender, or you could see it as the universe quietly nudging us toward a different relationship with distance. We are allowed to see almost unimaginably far. We are allowed, with enough effort, to send tiny messengers a little way into the darkness. But the project of physically occupying remote parts of the cosmos, of treating the galaxy as a playground for bodies like ours, runs up against layer after layer of cost. At small scales, fuel and engineering dominate. At larger scales, time dilation and human psychology join in. At the largest scales, cosmic expansion and horizons take over, redshifting distant galaxies into oblivion and placing whole regions forever beyond reach. None of these are moral judgments. They are simply what it looks like when you ask, within our best theories, how far can a worldline like ours be stretched? For now, the honest answer seems to be, not very far, in the grand scheme of things. Far enough to send probes beyond the edge of our own planetary system. Perhaps, one day, far enough to send small crews or their descendants to a handful of nearby stars. Never far enough to cross the universe in any simple sense, because there is no single static universe to cross. There is only a changing space-time, in which some destinations are receding faster than any ship can sail. The universe, in other words, does not slam a door in our face. It simply places the handle at a height that forces us to ask, each time we reach for it, what we are willing to give up in order to step through. Some doors you reach for and miss. Others you never touch at all, because something invisible has already decided how far your hand is allowed to go. Speed feels like one of the simple things. You press the accelerator. The car goes faster. You pour more fuel into a rocket. It climbs higher and moves more quickly. The story in our heads is straight. More push, more speed, no deep surprises. Relativity quietly replaces that story with another one. In Einstein's picture, there is a maximum pace at which cause can follow effect. Light in a vacuum moves at that pace. Every flash, every radio signal, every gravitational whisper propagates at that speed, and no faster. It is not just a fast thing among other fast things. It is woven into the structure of space-time itself. You are always compared to that speed, whether you ask for it or not. At low velocities, that comparison does not bother you. Drive along a highway at 100 kilometers per hour, and nothing in your body hints that any fundamental limit exists. Even a spaceship in low Earth orbit, circling the planet in about 90 minutes, still behaves in a way that feels comfortably Newtonian most of the time. You can add speeds, subtract them, boost a little more, and your intuition mostly works. Push harder, though, and the bookkeeping changes. As an object with mass approaches the speed of light, the energy required for each small increase in speed grows. At first, this growth is gentle. Later, it becomes steep. Near the limit, it turns brutal. To nudge a particle from, say, 99% to 99.9% of light speed already demands a huge jump in energy. To add another 9 in that chain costs more again. The closer you lean toward the wall, the more the wall pushes back. This is not a matter of engineering clumsiness. It is written into the equations. In special relativity, the kinetic energy of a moving particle depends on a factor that grows without bound as its speed approaches the speed of light. That is the mathematical shadow of the glass wall. To actually reach light speed, you would need infinite energy, infinite fuel, infinite patience. The universe does not have those to give, so it offers something else instead. When you pour more and more energy into a ship that is already very fast, most of that energy stops going into speed. It goes into time. From the ship's point of view, clocks on board still tick normally, heartbeats stay regular, processes unfold as they should. But compared to clocks left behind, everything on the ship slows. This is time dilation. In that sense, as you push the accelerator in the relativistic regime, you are not buying much extra speed through space. You are buying a different relationship to time. There is a way to picture this that stays close to the geometry from earlier. Draw space along a horizontal line and time along a vertical one. The world line of someone standing still is almost straight up. The world line of someone walking gently leans away from the vertical. As their speed increases, the line tilts more. The world line of a light beam sits at the maximum possible tilt, halfway between straight up in time and straight sideways in space. Relativity says no massive world line can ever tilt beyond that boundary. You can lean toward it, closer and closer, but never match it. The more you lean, the less of your motion is spent climbing upward in time. Your proper time, the time measured by your own clock, accumulates more slowly between shared events than it does for someone who stood still. From your perspective, you are always moving normally. It is others who rush ahead or fall behind. From the point of view of spacetime as a whole, these are just different angles carved through the same structure. Particle accelerators make this concrete in a way that no thought experiment quite can. In rings like the Large Hadron Collider, protons are whipped around to speeds so close to the speed of light that quoting all the nines becomes tedious. Their kinetic energies are enormous, far beyond those of particles in ordinary matter. Yet, no matter how scientists tweak the magnets and power supplies, those protons never outrun light. They only skim incrementally closer to its pace, and their internal clocks slow relative to the lab frame. Something similar happens naturally in the sky. High-energy particles from space, cosmic rays, strike atoms in the upper atmosphere and create showers of short-lived particles like muons. At rest, muons decay in a tiny fraction of a second. Traveling near light speed, their internal clocks run slow. Many survive long enough to reach detectors at the surface, where, without relativity, almost none should exist. Their arrival is an ongoing, quiet experiment that says, the wall is real, and the way you feel it is through time. For extreme travel, this offers both a possibility and a warning. The possibility is straightforward in outline. If you can accelerate a ship to a speed very close to the speed of light, then from the crew's perspective, distant stars come within reach in a manageable span of subjective time. A journey that would take centuries as measured on Earth might take decades or even years on board, because the crew's clocks are running slow relative to the outside universe. The warning sits in the same sentence. Those centuries still pass elsewhere. Civilizations evolve, falter, rebuild. Environmental crises unfold. Languages drift. You use the glass wall not to outrun light, but to outrun history. When you come back, if you ever do, you arrive not simply at a different place, but in a different era. The cost of leaning hard against the limit is to let go of synchrony with the world that launched you. This is why stories about near-light speed travel so often carry a note of estrangement. The physics does not forbid you from pressing your hand against that transparent boundary. It simply refuses to let you do so without falling out of step with almost everyone you know. There is a further, subtler cost. As speeds rise, kinetic energy climbs, and with it, the violence of even tiny impacts. A grain of dust hitting a ship at a small fraction of light speed carries the energy of a shell. The interstellar medium, thin as it is, becomes an obstacle course of potential catastrophes. Shielding must grow thick. Active defenses must fire. Routes must be plotted through clouds you can barely detect from afar. Every extra 9 in your percentage of light speed multiplies the difficulty of keeping a fragile habitat intact. You can stand at the edge of this logic and dream of simply stepping around it. What if there were particles that always moved faster than light? What if certain exotic configurations of spacetime allowed information to slip past the wall? Theories have played with such ideas. Hypothetical faster-than-light particles, tachyons, would always stay beyond the light barrier. Some solutions to the equations of general relativity, like particular warp drive metrics, seem to permit superluminal effective motion by contracting space in front of a vessel and expanding it behind. But each of these conjectures brings in new problems. Tachyons, if they exist, tend to destabilize the quantum fields they inhabit. Warp drive solutions demand forms of matter with negative energy density and enormous integrated energy requirements that border on the absurd. When you try to build a machine that outruns signals in the surrounding spacetime, you often find that you have also built a machine that can scramble cause and effect, sending information into someone's past and opening the door to paradoxes. The universe seems to tolerate dreams that lean toward the wall. It is much less accommodating when you try to punch through. So, the speed of light becomes more than a number in a textbook. It is the slope of the brightest lines in the space-time diagram. The edge of every light cone. The boundary of what can influence what, without breaking the story of causality. For a worldline like yours, made of ordinary matter, it is a surface you can approach, exploit, bargain with, but never cross. When people speak casually about breaking the light barrier, they are telling a Newtonian story in a non-Newtonian world. In the actual structure we inhabit, there is no knob you can turn to toggle between slower than light and faster than light. There is only the open region beneath the wall, and the wall itself, occupied by radiation and gravitational waves and nothing with rest mass. Extreme travel, in this light, is not about beating a record. It is about deciding how close you are willing to go to that boundary, knowing that each step closer brings disproportionate consequences. Stay far below. And journeys are slow but familiar. Time passes at nearly the same rate for everyone involved. Communication can keep up. Culture and travelers remain roughly in sync. Creep closer, and you start to buy distance with separation. Go all the way to the edge, and you trade almost all of your shared timeline for the ability to cover vast gaps in your own lifetime. The universe does not step in to stop you. It does not impose a curfew. It simply ties together energy, speed, and time in such a way that you cannot optimize all three. You can have high speed and low personal aging, at the cost of drifting far ahead of those who stayed. You can have shared time and safety, at the cost of remaining local. What you cannot have is a ship full of ordinary matter that flickers from here to there faster than light, while keeping everyone's story lined up. We call that a limit. It might be more honest to call it an invitation to decide what kind of journey we actually want to make. Some limits you meet in thought. Others you brush against with your own body, without meaning to, and only later learn their name. We talk about time travel as though it were a lottery ticket that nobody has ever won, a fantasy reserved for films and late-night conversations. But the universe has been bending time around us, quietly and precisely, for as long as we have been measuring it. It is just not doing it in the way most stories promised. Long before anyone sat on board a starship, physicists started carrying timepieces onto ordinary planes. In the early 1970s, two researchers, Joseph Hafele and Richard Keating, took a set of atomic clocks and flew them around the world on commercial flights. They sent some eastward, in the direction of Earth's rotation, and some westward, against it. On the ground, a reference clock stayed behind in a laboratory. When the flying clocks returned, every one of them disagreed with the one that had never left. The differences were tiny, but they matched the predictions of relativity. Speeds and altitudes that felt mundane to the passengers had been enough to make time itself diverge. From the point of view of the clocks, nothing special had happened. Each one simply sat in its casing, letting atoms tick in their regular rhythm. From the point of view of space-time, their world lines had taken slightly different paths. some higher in the gravitational field, some moving faster over the ground. That was enough. Each path accumulated a different amount of proper time between departure and landing. That experiment was more than a curiosity. It said, in a way that could not be ignored, that how long something lasts is not absolute. It depends on the route it takes through the geometry. The most pervasive proof sits in your pocket or on the dashboard of your car. The Global Positioning System uses a constellation of satellites orbiting tens of thousands of kilometers above the Earth. Each satellite carries an atomic clock. Those clocks do not tick at the same rate as clocks on the surface. High above the ground, gravity is slightly weaker, which makes their time run a bit faster. At the same time, the satellites move rapidly along their orbits, which makes their time run a bit slower due to their speed. Both effects are small. Together, they are enough that, if we ignored them, your phone's estimate of your position would drift by kilometers each day. The system works only because engineers constantly correct for relativity. They pre-adjust the satellite clocks before launch. They account for the daily drift. Every time you use a map application to find a cafe or navigate a highway, your trajectory through the city depends on the fact that time is not uniform between different heights and speeds. That is already a form of time travel, although we rarely call it that. You place clocks in different gravitational potentials and different states of motion. You let them separate for a while. When you bring them together again, they tell different stories about how much time has passed. Laboratories have pushed this effect into even more intimate scales. Take two ultra-precise atomic clocks and place one slightly higher than the other, separated not by mountain ranges but by a difference of height you could cover in a small staircase. Let them run. After a while, the higher clock, sitting in slightly weaker gravity, has ticked ahead. The lower one has fallen behind. General relativity does not care about human expectations of what should count as the same place. It cares only about the shape of space-time, and that shape changes continuously with height. In orbit, astronauts feel time differently again. On the International Space Station, crews live for months at a time, circling the planet roughly every hour and a half, moving at many thousands of kilometers per hour. Their clocks experience both sides of relativity at once. They are high up, where gravity is a bit weaker, speeding their time. They are also moving quickly, slowing it. The net result is that, compared to people on Earth, their accumulated proper time differs by tiny amounts. When they return, their bodies have aged a little less than those of their identical age mates on the ground. For most missions, the difference is a fraction of a second. In the mid-2010s, when astronaut Scott Kelly spent close to 1 full year aboard the station while his twin brother Mark stayed behind, this became an object of study. NASA treated it as a rare chance to compare two almost identical biological systems that had experienced different environments and slightly different trajectories through spacetime. The most visible changes were biological and psychological. Underneath those, tucked into the same equations that guide satellites and atomic clocks, their world lines had diverged by a measurable, if tiny, amount of time. All of this is modest. No one steps into a capsule, flips a switch, and appears in the far future. No paradoxes emerge. These are shifts measured in nanoseconds, microseconds, perhaps milliseconds over a whole lifetime. They matter for navigation, for scientific precision, for tests of theory. They do not yet matter for how it feels to be alive. But the logic does not stop at small scales. If you can generate these differences with aeroplanes and satellites and space stations, the same equations say you can amplify them with more extreme journeys. Imagine a ship that can accelerate at a steady, comfortable fraction of Earth's gravity for months on end. The crew feels a constant pull on their feet. They move around as on a tilted floor that pretends to be a planet. As the engines push them toward a significant fraction of light speed, several things happen at once. Outside, in the rest frame of the launching civilization, the ship's acceleration tapers off as practical limits are reached. Inside, the crew still feels that steady weight. Their time, measured by their own bodies and their onboard clocks, flows smoothly. From their perspective, they could cross tens or hundreds of light years in a span of years or decades, stars that would be unreachable within any single human life. If we insist on staying nearly at rest, slide past their windows. The cost is that the universe they left behind races ahead without them. When they slow down again and establish contact, the gap is immense. Centuries, perhaps longer, have passed on the worlds that built their engines. This is not science fiction ornament. It drops out of the same mathematics that govern the global positioning system. Travel fast enough, long enough, and your 1 hour does not match the 1 hour of those who stayed behind. Push the parameters far, and the mismatch becomes huge. In that sense, traveling to the future is not forbidden. It is simply bound to a mechanism that offers no return. You can slow your own passage through time relative to another reference frame. You can use that to leap forward in their history. What you cannot do, according to every tested piece of relativity, is come back to an earlier slice of their worldline, or of your own. The geometry of spacetime allows angles and tilts and differences in accumulated length along a worldline. It does not allow that line to fold back on itself without introducing deeper troubles with causality. The phrase, time travel is real, can feel dishonest because we are so used to attaching it to stories of backward journeys and altered pasts. But there is a quieter reading that is already part of daily life. Our experience of duration is path-dependent. We already inhabit a universe where twins can genuinely age differently if their lives take distinct routes through gravity and motion, even if in practice we have only nudged that effect. From a human point of view, the important question is not whether the effect exists, it is what we would do with it if we could scale it up. Would anyone step onto a ship knowing that, while they might feel only 10 years pass between departure and arrival, their children and grandchildren would live and die in the meantime? Would any government or culture willingly send crews on missions whose success would be judged by people who do not yet exist? In societies, no one can predict. At what point does visiting the future become indistinguishable from self-exile? There is also the other direction, the subtle ways we are already being carried without choice. Clocks higher up in a city run a little faster. People who spend more time flying at high altitude age, very slightly, differently from people who rarely leave the ground. The differences are too small to feel, too small to affect any single life. Still, they hint at a strange fact. Even without deliberate technology, the universe is gently peeling our world lines apart. Stand by a window in a tall building and think of the clock on your phone, ticking a touch faster than one resting on a table in the basement. Live your life in a valley or on a mountain plateau and you inhabit a slightly different temporal flow. None of this changes what you remember or how you love. It does remind us that time is not a river sweeping us all along at a fixed rate. It is more like a field of tiny currents, shaped by mass and motion, that we mostly do not notice because they almost cancel out in daily life. Extreme travel would turn those tiny currents into rapids, near a black hole. The curvature of space-time is so intense that an object hovering just outside the point of no return experiences time that is hugely slowed compared to a distant observer. Stay there for what feels like an hour, and the outside universe could race ahead by years, centuries, more, depending on how close you sit and how stable your orbit is. In principle, with the right engines and shielding, you could use such a region as a one-way gate to the far future of the cosmos itself. Again, relativity does not forbid this. It simply ties it to physical conditions that are almost impossible to survive and to engineering challenges far beyond anything we now know how to handle. The mechanism, though, is the same one that makes a satellite clock drift and a laboratory clock on a higher shelf tick faster. Stretch the geometry enough, and the difference in accumulated proper time becomes enormous. When you start to see all these cases as points along a single curve, the notion of time travel loses some of its magical glamour and gains something colder. It becomes a question of how far you dare to separate your personal sense of now from the now of everyone and everything else. You can move a little way along that axis by flying, by orbiting, by sitting higher in a gravitational field. You can, at least in principle, move much farther by approaching the speed of light or skimming close to extreme masses. Each extra step buys you more asymmetry between your timeline and the timeline of the rest of the universe. There are no shortcuts that let you jump backward to erase regrets or rescue earlier selves. There are only ways of choosing who or what you will be out of sync with. In that way, time travel of the kind our theories endorse is less a device than a question. How much misalignment can a person or a civilization tolerate? How large a gap between our now and their now can relationships survive? At what point does a traveler returning from a high-speed voyage or a near-horizon orbit become, for all practical purposes, a visitor from another age, carrying memories that belong to a world nobody else remembers? The universe has already given us the tools to begin answering those questions. They sit in experiments from the 1970s, in the software of navigation satellites, in the data from long-duration missions in low Earth orbit. We have not yet used them to leap centuries ahead. We have used them to draw a careful outline of the cost. And that, more than any paradox-free fiction, is what real-time travel looks like in a space-time that refuses to let you move without paying in more than fuel. Some places do not just stretch your time. They bend it so hard that, from far away, it seems to stop moving at all. A black hole begins, on paper, as a solution to Einstein's equations. Take enough mass. Squeeze it into a small enough region. The geometry of space-time responds by creating an area where all possible paths lead inward, inside a certain boundary, called the event horizon. No signal can escape to the outside universe. Not light, not matter, not information, at least in the simple picture. To someone watching from far away, anything that falls toward that boundary slows. Its signals are redshifted, stretched to longer wavelengths. Its clock appears to tick more and more slowly. In the limit, as it approaches the horizon, it seems to freeze. To the thing that is falling, nothing like that happens. Crossing the horizon, if tidal forces are gentle enough at that scale, feels locally ordinary. No sudden flash, no physical wall. You drift inward, and after some finite time measured by your own clock, you reach regions where the curvature grows so strong that no known form of matter can withstand it. World lines that once gently diverged are crushed together. In the simplest models, they end at a singularity. A point where the mathematics that carried us this far no longer gives sensible answers. This mismatch between outside and inside viewpoints is one of the reasons black holes feel like places where time breaks. For distant observers, nothing ever quite slips through. For infalling observers, crossing and destruction happen in a finite, personally ordinary interval. For decades, black holes lived mostly in the realm of theory and indirect inference. Astronomers gathered clues. Stars in tight orbits around dark companions, X-ray emissions from gas spiraling into unseen depths, energetic jets shooting from galactic centers. The behavior pointed to massively compact objects that fit the predictions of general relativity better than anything else we know. Then, slowly, the universe started showing us more. One example sits in the galaxy Messier 87, in the constellation Virgo, tens of millions of light-years away. At its core is a black hole with a mass of billions of suns. For a long time, it was an abstract piece of data in catalogs, a suspected engine driving bright jets and intense emissions. In the second decade of the 21st century, a loose global network of radio telescopes linked together to form the Event Horizon Telescope. By synchronizing dishes across the Earth and observing at very short radio wavelengths, they effectively created a planet-sized instrument. In April of 2019, the collaboration released an image that quickly became part of our shared mental furniture, a blurry ring of glowing gas with a dark center. That central darkness was the shadow of the black hole in Messier 87, carved out by light rays that had been bent and swallowed by its gravity. The picture did not show the event horizon directly. It showed how light behaved in a region where space-time curvature is strong enough that even small changes in position produce large changes in where photons end up. It was a way of seeing the shape of time near the edge. Around the same period, another set of instruments started listening to the universe in a different way. Interferometers like LIGO and Virgo use laser beams along long perpendicular arms to sense tiny changes in distance, smaller than the width of a proton, caused by passing gravitational waves. In September of the mid-2010s, they detected a signal that matched the predicted chirp from two black holes spiraling into each other and merging. The discovery was announced months later after careful checks. It was the first time we had directly heard the ringdown of spacetime itself after such a collision. These observations do more than add drama. They confirm that the extreme objects in our equations really exist out there, sculpting the flows of matter, light, and time in the universe. Near a black hole, the geometry is not just curved, it is curved in a way that radically separates experiences. Consider a spacecraft that hovers just outside the event horizon of a large, non-rotating black hole, firing its engines constantly to resist the pull. Far away, back in quiet space, Mission Control tracks its clock. As the craft approaches the horizon, the signals from its clock arrive more and more slowly. Radio messages stretch. Light pulses shift toward the red. To Mission Control, the craft seems to approach a standstill, frozen just above the edge. On board, the crew feels continuous time. Their hearts beat. Their instruments tick. If their engines fail, they do not hang there forever. They fall in. Crossing the horizon takes a calculable, finite span of proper time, depending on their path. Their story continues, just increasingly cut off from any external retelling. In principle, you could use this behavior to turn a black hole into an extreme one-way time machine. Arrange for a trajectory that threads just outside the horizon, staying in the region of intense time dilation for as long as your engines and hull can tolerate. Then fire hard and escape back to more gently curved space. From your point of view, the excursion might last minutes or hours. From the point of view of a distant observer who receives your returning signal, many years, centuries, or in the case of the most extreme orbits, billions of years could have passed. You emerge into a universe that has aged far beyond the one you left. Galaxies more dispersed by cosmic expansion. Star formation dwindled. Backgrounds cooler. You have traveled into the deep future by taking a path through space-time that hugged a region of extreme curvature. This is not a plot device grafted onto black holes. It falls out of the same general relativity that predicts the orbits of planets and the existence of gravitational waves. The obstacle is not permission. It is survival and engineering. Real black holes are not calm, isolated spheres. They are often surrounded by accretion disks, rings of gas and dust heated to high temperatures as they spiral inward. Magnetic fields thread the region, guiding jets of particles that can extend far beyond the host galaxy. Radiation levels near these structures can be lethal. Tidal forces, the difference in gravitational pull between the near and far sides of your body or your spacecraft, can stretch and compress objects so violently that the evocative term spaghettification is not much of an exaggeration. For a stellar mass black hole, the kind formed by the collapse of a massive star, the event horizon might be only a few tens of kilometers across. To get close enough for extreme time dilation without crossing it, you would need to park your ship in a region where the gradient in gravity from nose to tail would crush it. Supermassive black holes, like the one in Messier 87 or the one at the center of our own galaxy, are gentler at the horizon. Their huge mass spreads the tidal forces over a larger distance. That makes skimming possible in principle, but does not make the environment friendly. Even tiny errors in navigation are unforgiving. A slightly miscalculated burn, a burst of radiation that disrupts your guidance system, an unexpected clump of infalling matter changing the local structure of space-time. Any of these could shift your worldline from one that loops back out to one that crosses the horizon. After that, no external rescue is possible. All of this makes black holes perfect embodiments of the pattern we have been circling. The universe does not forbid certain kinds of extreme travel. It simply couples them to conditions that test the limits of matter, information, and human judgment. There is another layer to the story, one that has occupied theoretical physics for decades. What happens to information that falls in? In the simplest view, anything that crosses the event horizon takes its details with it. From the outside, all that matters are the black hole's mass, charge, and spin. This led to a famous phrase, "Black holes have no hair," meaning no surface features encoding complex information. But quantum theory is very strict about information. It does not like the idea of it simply vanishing from the universe. If black holes destroy information, then fundamental principles of quantum mechanics are violated. This tension is called the black hole information paradox. Many proposed resolutions have been suggested. Subtle correlations in the outgoing radiation as black holes slowly evaporate through quantum processes. Holographic ideas in which information is stored on a lower dimensional boundary. Descriptions where the interior and exterior quantum states are linked in ways that avoid outright loss. None of these have yet been confirmed by observation. They show how a very concrete question about falling into a black hole forces us into deep, unresolved parts of our theories. From our point of view, the important thing is the pattern. Here is a kind of extreme journey the equations appear to allow. A plunge into a region where time and space swap some of their roles. Where world lines once pointed outward, now can only converge. The cost is that, once you commit, your story exits the visible universe. Even the question of whether the detailed pattern of your matter and memories persists in some encoded form becomes a battleground between different views of physics. Films like Interstellar borrow these ingredients. In one of its most discussed sequences, a crew visits a planet that orbits close to a fictional black hole. The gravitational field there slows time so much that hours on the surface correspond to many years for the ship that waits farther away. When the explorers return, their crewmate has aged. Messages from home cover decades, and a large portion of one character's life has played out off-screen. The details of the scenario are tailored for drama, but the underlying concept that a strong gravitational field can create enormous differences in elapsed time between two paths is straight from the theory. What such stories tend to soften is the sheer precariousness of operating near those boundaries. Real black holes do not sit isolated in quiet planetary systems, offering stable perches for extended visits. They live in dense stellar clusters and galactic cores, surrounded by violent flows of plasma. The precision required to dip in and climb back out, with a human crew intact, is beyond anything we can seriously plan for now. Yet the mere existence of these objects tells us something sharp about the universe's attitude to extreme travel. It is willing to create natural laboratories where time behaves in ways our everyday experience barely prepares us for. It is willing to host structures where a world line can point so steeply toward the future that the rest of the cosmos races ahead unseen. It is not willing to make those laboratories easy to use or to put clear labels on what happens inside. Stand back from the mathematics for a moment and think of a black hole as a region in the space-time block where a great many world lines simply end. For the rest of the universe, those lines terminate at the horizon, fading as their last signals stretch away. For the objects themselves, the lines continue into a part of the structure that no external observer can enter and then report from. In a block universe picture, both the infall and the end are already part of the whole. From our embedded, local perspective, they mark the places where prediction and reconstruction hit a wall. So when we say that black holes are places where time breaks open, we are not gesturing at supernatural fractures. We are acknowledging that, in these regions, the rules we have traced elsewhere come together in their most uncompromising form. Paths into the deep future, one way. Boundaries that divide what can be causally connected from what cannot. Questions about information and identity that the current state of physics cannot fully settle. The universe does not post a warning sign at the edge of such a region. It simply shapes space-time in a way that asks, with more force than usual, whether crossing is worth what it removes from you and what it removes from the view of everyone who stays outside. Standing in front of a border that only lets you through one way, the next question almost asks itself, is there another route? If space-time is a structure, not a simple stage, it is tempting to treat it like paper. You take a sheet. You mark 2 points at opposite corners. The straight line between them is long, then you fold the sheet so those 2 points touch. You draw a different line, now almost invisible in length. That is the picture people reach for when they talk about wormholes. In physics language, a wormhole is a connection between two distant regions of space-time. A tunnel that links points that would otherwise be far apart. You enter through one mouth, you travel a short internal distance. You exit somewhere else that, from the outside, appears separated by huge stretches of space and time. To someone inside, the journey feels local. To someone outside, you have done something that seems to ignore the usual rules of distance. The first versions of this idea did not come from film scripts. They arose inside general relativity itself. In the early 20th century, Einstein and Nathan Rosen studied a mathematical construction that joined two copies of the same spacetime along a bridge. Later, people called this an Einstein-Rosen bridge. It looked, on paper, like a wormhole, but the details were not friendly. That bridge was not stable. Any attempt to cross it caused it to pinch off too quickly for matter to get through. As a passage, it failed. As a signpost, it was important. It said, if you treat space-time as a flexible geometry, there are ways to join distant regions that are stranger than simple curves. Decades later, Kip Thorne and Michael Morris turned the question around. Instead of asking what general relativity happened to allow, they asked what would be required for a wormhole that a traveler could actually survive. They wrote down a class of geometries that kept the tunnel open, with gentle enough tidal forces at the throat that a human-scale ship could, in principle, pass without being torn apart. The price was severe. To hold such a wormhole open, the stress and energy in the throat region had to violate what physicists call the classical energy conditions. In simpler terms, you would need matter with negative energy density, as seen by some observers. Ordinary matter does not do this. Neither do familiar forms of radiation. The equations were not saying build this with steel and fuel. They were saying if you can produce and configure something that behaves in a way nothing we know behaves, this structure could exist. There is a small foothold for hope, and it comes from quantum theory. In the mid-20th century, Hendrik Casimir studied what happens when you place two uncharged, perfectly conducting plates very close together in a vacuum. Quantum fields in the region are constrained by the boundary conditions, and the vacuum fluctuations between the plates differ from those outside. The result is a tiny attractive force between the plates, as though the vacuum itself were pushing them together. The energy density in that gap is, in a certain sense, lower than the surrounding vacuum. People sometimes point to this as an example of negative energy. It is not the exotic matter of science fiction. The effect is incredibly small and very delicate, but it hints that nature, at the quantum level, allows brief, tightly controlled violations of the classical energy conditions. That is not a recipe. It is more like a whisper. It says the door to wormholes is not slammed entirely by classical physics. It is wedged open a crack by quantum behavior. Exploiting that crack is another matter. Popular stories tend to skip the engineering and head straight for the image. A smooth, dark sphere hanging near a planet, its surface reflecting starlight with a strange lensing distortion. A ship dives into that surface and emerges near another star, in another galaxy, or in another universe entirely. Time outside barely notices. Time inside passes like an ordinary trip through a tunnel. This is close to how the film Interstellar presents its wormhole near Saturn. The story leans on the Morris-Thorne geometry, assuming that some advanced intelligence has already done the impossible work of stabilizing the tunnel. The crew simply uses it. Our actual equations are not that generous. Even granting the existence of exotic matter, traversable wormholes are precarious. The throat region, where the shortcut lives, is a place where small disturbances can grow. Quantum fields fluctuating there can, in some analyses, produce feedback that destabilizes the tunnel. A tiny change in the energy flowing through the wormhole can trigger collapse, snapping the connection shut. A traveler inside, when that happens, might be crushed or stranded. The two mouths could pinch off from each other and form separate black holes. Alternatively, the geometry could twist in other ways that we do not yet fully understand. Because our tools for handling quantum fields on strongly curved backgrounds are incomplete. Even if the throat holds, The surroundings can be hostile. Near each mouth, space-time may be highly curved. Tidal forces could compress and stretch matter. Streams of infalling gas, radiation from nearby stars, or interactions with dark matter could all complicate the environment. A careless approach, at the wrong angle or with the wrong speed, could lead to catastrophic heating or fragmentation of the ship long before it ever reaches the shortcut proper. There is also the question of how you aim. In the simplest visualizations, a wormhole has two mouths connected by a symmetric throat. You decide where to place each mouth. You keep them anchored. You maintain their stability. In a real universe filled with gravitating matter and dynamic fields, those mouths would feel forces. Orbits would shift. Encounters with other masses could tug at the geometry. Over long periods, a network of wormholes would need constant adjustment to keep entrances where you expect them to be. If they drift, routes could terminate in dangerous places. Inside dense molecular clouds, near neutron stars, deep in potential wells, where escaping again would cost enormous amounts of energy. A miscalculated endpoint could place the exit below the surface of a planet. The tunnel would then open into rock or ocean or atmosphere under pressure, with predictable results for anything trying to use it. Even in a perfectly controlled setting, any serious deployment of wormholes would create new strategic landscapes. If you can connect two distant points in spacetime with a short path, you can transport goods, people, and information. You can also transport weapons. A civilization that controls a network of such shortcuts would have an immense advantage over one that does not. War and politics would be reshaped. So would crime. Smuggling would no longer be about slipping past borders. It would be about secret mouth locations. Diplomacy would need to account not only for territories in ordinary space, but for ownership and regulation of these tunnels. Who is allowed to build one? Who monitors their use? Who has the authority to shut them? An accident in such a network would not look like a crashed plane. It could look like a burst of radiation and debris suddenly appearing in an inhabited region because a wormhole endpoint was misconfigured. A sabotage event would not need to physically cross a front line. It would only need to compromise the throat conditions enough to destabilize the connection at the right moment. All of this assumes that the challenge is only technical and political, but at the level of physics, wormholes also touch causality. If you take one mouth of a traversable wormhole on a high-speed journey and then bring it back, the difference in proper time along its path compared to the path of the other mouth can, in some models, create a situation where a traveler entering one mouth exits the other at an earlier external time. That turns the wormhole into a potential time machine, with all the paradoxes that come with it. Quantum effects near such configurations seem to threaten their stability, as though the universe were trying to enforce chronology by punishing shortcuts that loop back on themselves. Some recent ideas have tried to soften this. The conjecture nicknamed equals EPA suggests a deep connection between entanglement in quantum mechanics and wormhole-like links in spacetime. In certain carefully constructed models, information can be described as passing through a kind of quantum wormhole, without allowing any actual faster-than-light communication or causality violation. These are stylized, lower-dimensional systems, not blueprints for macroscopic travel. They show that the boundary between geometry and quantum information is subtler than we once thought. From the perspective we have been keeping, the pattern is familiar. Start with the desire to reach distant parts of the universe without paying the usual price in travel time and fuel. Translate that desire into the language of space-time geometry. Find that, in principle, there are arrangements that do what you want. Then discover that every such arrangement demands ingredients that stretch or exceed everything you can reasonably hope to obtain. Energy densities outside the range of any known process. Control over quantum fields at a level we are nowhere near. A tolerance for geopolitical and ethical risks that most societies would find hard even to discuss with a straight face. And hovering behind all of this, the same question that black holes posed in another form. If we could somehow meet these demands, what kind of life would grow around such tools? Who would step into tunnels that might collapse if a single calculation were wrong? Who would trust that the mouth marked home still opens where it did yesterday? in a universe where even ordinary orbits shift over time. The universe, in its equations, does not laugh at the notion of a wormhole. It quietly allows certain shapes of geometry that, given outrageous conditions, would act as shortcuts. At the same time, it couples those shapes to requirements that look less like an invitation and more like a test. How badly do you want to join distant points? How much impossibility are you prepared to wrestle with? How many new forms of danger are you willing to accept in exchange for a tunnel through space-time? In the end, wormholes sit in a strange place between fantasy and law. They are not pure invention. They are shadows cast by general relativity and quantum theory onto the wall of our imagination. Whether any civilization ever manages to grab those shadows and give them weight is an open question. What is clear is that if the universe does permit that leap, it will not be because the price turned out to be low. And even if we could afford that leap, there is a quieter bill we have not paid yet. What happens to the order of events that makes a story make sense at all? Causality sounds simple. A match lights. Smoke rises. You speak a word. A microphone vibrates. The signal travels, is recorded, played back. Somewhere underneath every intuition about time is this idea that causes sit in the past and effects unfold in the future. In that order, for everyone who can meaningfully compare notes. Relativity complicates the details but keeps that core. Different observers may disagree about how far apart in space two events are, or even whether they were simultaneous. They do not disagree about which event could have influenced which, as long as nothing outruns light. The light cone structure of spacetime, the pattern that says what can lie in the future or past of what is rigid. You and I can move our world lines around inside that pattern. We can lean closer to the cone's edge by going fast. We can bend our paths near massive objects. But as long as we never cross the boundary defined by light, the fundamental order of this can make that happen survives. The trouble begins when we ask for more. Once you have wormholes on the table, or any other mechanism that might connect distant points in spacetime, it is natural to ask whether you can not only jump across space, but also cheat the ordering of time. You take one mouth of a wormhole, you accelerate it to high speed and then bring it back. Because of time dilation, the clock at that mouth lags behind the clock at the mouth that stayed put. Now, locally, going through the tunnel from the younger mouth to the older one looks like stepping into a corridor and out again. Globally, the spacetime diagram suggests that you have gone from a later event to an earlier one. Close that loop carefully, and you can sketch a world line that leaves a place, travels through ordinary space, enters a wormhole mouth, and emerges somewhere and somewhen that lies in its own past. That is what physicists call a closed time-like curve, a path through space-time that always moves forward according to the traveler's own clock, yet winds up back where it started. On paper, general relativity does not scream when you write down such curves. Certain exact solutions, like the rotating universe described by Kurt Gödel or the hypothetical infinitely long spinning cylinder studied by Frank Tipler, contain them naturally. In these models, the geometry twists time around itself so that, if you follow a particular route, you eventually return to an earlier moment. The catch is in the words infinitely long, rotating universe, and particular route. These spacetimes are strange even before you add time machines. The Tipler cylinder, for example, requires a massive object spinning so fast and stretching so far that it is hard to imagine how the universe would ever produce it, or how any finite civilization would build it. The Gödel universe does not match what we actually see when we map cosmic expansion. Still, the existence of these solutions keeps the question open. If the equations that govern gravity so easily accommodate worlds where closed time-like curves are possible, why does our world seem so hostile to them? The cleanest way to feel the tension is not to worry about exotic cylinders. It is to tell yourself a very small story. You receive a message from your own future. It arrives with instructions and some verifiable prediction about the stock market or political events, or personal details that convinces you it is genuine. The message says, "On a certain date, you must send exactly this data back, using a device you have not yet built, or else the chain breaks." You follow the script. You spend years of your life developing the machine, waiting for the moment, sending the packet. The day after you succeed, something goes wrong. The lab burns down. The records are lost. In the new timeline, no message ever leaves, but you received one. The paradox sits there, plain. If the message never goes back, how did it arrive? If you prevent its sending, you destroy the conditions for its existence. If you do not prevent it, you seem to have created information with no origin, looping endlessly around a curve in space-time. The famous grandfather paradox is the same, not with more emotion. You travel to your own past. You prevent an ancestral relationship that led to your birth. If you succeed, you erase yourself. If you erase yourself, who did the traveling? These puzzles are not just logical games. They expose a clash between the way we normally think of history and the kind of paths general relativity, taken literally, sometimes seems to allow. Various responses have been proposed. One is to sacrifice a certain kind of freedom. The Novikov self-consistency principle says, roughly, that if closed time-like curves exist, the only histories that actually occur are those that are globally consistent. You can travel to the past, but every action you take, there was always part of the story. You can push events around locally, but you can never change the overall script. In this view, the universe is like a book whose pages you are allowed to walk back and forth through. You can read earlier chapters. You can even appear as a character in scenes you once thought did not include you, but you cannot rewrite the printed text. Any attempt to create a paradox automatically fails. The gun jams. The letter goes astray. The stock advice you offer to your younger self was, all along, the reason things unfolded exactly as they did. There is a certain austere charm to this. It protects causality from explosion by tightening it into a loop. It also raises uncomfortable questions about choice. If your future visit to the past must happen in a way that preserves consistency, then, from the perspective of the entire space-time block, there was never any chance you would decide otherwise. The feeling that you could have refused the mission, stayed home, or acted differently becomes, at best, a local illusion. Another response, more aggressive, is to suspect that something in our theories breaks down whenever we try to create closed time-like curves. Stephen Hawking expressed this as a chronology protection conjecture. The idea is that quantum effects, neglected in simple classical solutions, grow large. Near would be time machines. Vacuum fluctuations pile up. Energies diverge. The region of space-time becomes unstable and collapses, or otherwise rearranges itself before a closed time-like curve can fully form. On this picture, the universe has a kind of built-in veto. You can twist geometry quite far. You can create extreme gravitational fields. You might even be able to build wormholes of a sort. But as soon as you start setting up a configuration that would let a Worldline loop back and influence its own past, quantum fields act like a fuse blowing. The device fails. Not because of mechanical error, but because the deeper layers of reality refuse to support that pattern of events. We do not yet know whether chronology protection is really how things work. The calculations involved are precarious, because they live in the messy zone where gravity and quantum theory overlap, a zone we do not fully understand. What we do know is that every concrete attempt to design a time machine within known physics runs into some barrier. Unphysical matter, unstable solutions, or energies that become unmanageable. A third response shifts the problem sideways rather than blocking it. In the many worlds interpretation of quantum mechanics, every measurement or interaction that has multiple possible outcomes leads, in effect, to a branching of the universal state into different, non-communicating sectors. Apply that idea to time travel, and one way out appears. When you go back and change something, you do not overwrite your own history. You slide into a branch where that change was always part of the story. In that setting, you can meet your younger self and radically alter their path, You can prevent your own birth in that branch. You can cause or avert disasters. None of it produces paradox, because the self who stepped into the machine came from a different branch whose history remains untouched. The cost is that you can never return to the actual past that made you. You can only visit cousins of it in a larger multiverse. From a narrative point of view, that solves the knot. From an existential one, it undercuts the fantasy that drives many of our questions about the past. What people often want is not to spawn alternate versions of reality. They want to repair this one. Physics, so far, offers no mechanism for that. There is an even simpler way to see why the universe might be so strict about backward travel. Allow faster-than-light communication in any form. And you can construct scenarios where messages loop into the past without any wormholes at all. Different observers, moving relative to each other, disagree about the order of events that are space-like separated. A signal that is instantaneous in one frame looks backward in time in another. With clever enough choreography, you can send a tachyonic message to someone who, from your own perspective, has not yet sent theirs to you. The mathematics is clear. If you have superluminal influences, you can build causal loops. If you forbid those influences, the loops cannot even start. The speed of light limit is not just an arbitrary number. It is part of the scaffolding that keeps cause and effect from snarling. So when we ask whether travel can break causality, what we are really asking is whether the universe ever lets that scaffolding be dismantled. The most honest answer our current theories give is perhaps in some carefully controlled, self-consistent, or branching sense, but not in the wild, omnipotent way that popular time travel stories suggest. You and I can strain at the leash of simultaneity. We can tilt our world lines, fall through intense gravity, or speculate about tunnels that join distant points. We cannot, as far as any tested physics indicates, kick a stone in 1990 and thereby erase the conditions that made the kick itself possible. There is a more personal side to this. The appeal of time travel to the past is almost never about causality diagrams. It is about regret and curiosity. The moment you wish you could revisit, the words you did not say, the disaster you would prevent. The temptation is to treat the past as a draft that could be edited if only the right technology appeared. A universe that protects chronology is, in a sense, refusing that wish. It allows you to travel into futures where your choices echo in ways you cannot foresee. It allows you to slow your own time relative to others, to become a stranger to your original world. It does not allow you to walk back into an earlier page of your own life and scribble over the ink. You can call that harsh. You can also see it as a condition for meaning. If past events were endlessly revisable, if every outcome could be retroactively patched, the link between action and consequence would blur. Responsibility would be hard to define. Memory would lose its anchor. What extreme travel seems to do, again and again, is stretch the connection between where and when without quite severing it. It lets you slide along timelines, or skip ahead, or peel away from your contemporaries. The cost, every time, is paid in separation and uncertainty, not in new powers over what has already happened. The problem of the past, then, is not just a technical challenge for speculative engineering. It is a boundary condition written into the kind of space-time that allows beings like us to ask questions at all. Physics lets us approach that boundary and trace its shape. It does not so far offer a doorway through. If the past is not a draft we can rewrite, that is not just a narrative choice. It hints that the universe carries its own defenses, built into the way events fit together. You can think of those defenses as three broad strategies. The first is to make paradoxical journeys extremely fragile. The second is to allow them only in forms that cannot change anything important. The third is to shift them into places that are, for all practical purposes, somewhere else. Start with fragility. In the last chapter, closed time-like curves were those loops where a traveler moves forward on their own clock, but eventually returns to an earlier point in space-time. On paper, they are easy to sketch. In a real universe filled with quantum fields, they may be almost impossible to stabilize, near any would-be time machine. Quantum fluctuations in the vacuum are not just background noise. They respond to the geometry. When you design a spacetime that squeezes light cones so that future and past can touch, quantum fields feel those squeezed regions and can pour energy into them. Calculations in simplified models suggest that, as a closed time-like curve is about to form, the energy density seen by some observers can diverge. In plain language, the region tries to flood itself with radiation. That radiation curves spacetime in its turn. It can grow strong enough to destroy the delicate arrangement of geometry that was about to produce the loop. The result is a kind of self-sabotage. The more you twist spacetime toward paradox, the more the vacuum itself pushes back. Stephen Hawking called this chronology protection. The idea is not that some external agent monitors time machines and smashes them. It is that the same quantum processes that give us ordinary phenomena like the Casimir effect also act as a fuse when causality is threatened. Attempt to build a device that lets you influence your own past, and you generate the instability that keeps it from ever completing. We do not yet have a full theory of quantum gravity, so this picture is incomplete, but it fits a pattern we see elsewhere. The universe allows structures that look dangerous in a purely classical analysis. Then, when you include more of the physics, those structures become either unstable or so constrained that their worst excesses are blunted. Black holes are one example. Cosmic censorship, another conjecture, suggests that the truly pathological parts of spacetime are hidden behind horizons, not exposed nakedly to the rest of the universe. Chronology protection is a similar instinct applied to time machines. The second strategy is self-consistency. The Novikov principle states, roughly, that the only histories that actually happen are those that are globally consistent. Even when closed, time-like curves are present, the universe does not forbid a traveler from entering their own past. It forbids them from changing it. In a self-consistent story, every attempt at a paradox fails for reasons that were always part of the script. You go back intending to prevent a catastrophe. Your actions, sincere and carefully planned, become the very cause of the event you were trying to avert. You attempt to kill your grandfather. Circumstances conspire so that your bullet misses or hits some other target that completes the loop. From the inside, this feels like frustration. From the outside, it is just a single fixed history, with no branches and no contradictions. Physics does not enforce this principle by fiat. It emerges in models where one asks, given a space-time with closed time-like curves, what solutions to the equations of motion for matter are possible? Often, the only solutions that exist are the consistent ones. Attempts to specify inconsistent initial conditions simply fail to produce any evolution at all. You can think of it as a kind of global boundary condition. Instead of setting initial data at one moment and letting everything flow forward, you must choose a whole pattern of events in space-time that fits both the local laws and the requirement that no contradictions arise. That pattern may leave no room for arbitrary choices in the regions where loops occur. For a human mind used to thinking of free decisions at each moment, this can be unsettling. It suggests that if time machines exist, then some of what we call choice is constrained by a consistency requirement we cannot see. For the universe, it is an efficient way to avoid logical breakdown without sacrificing every exotic geometry. It does not need to veto loops outright, as chronology protection would. It needs only to ensure that every loop is harmless in the sense that it never lets information spring from nowhere or disappear into impossibility. The third strategy uses multiplicity. In the many worlds interpretation of quantum theory, the universe does not choose a single outcome when a quantum event has several possible results. All of them occur, each in its own branch of a larger wave function. Decoherence, the process by which quantum superpositions become effectively classical mixtures when systems interact with their environment, ensures that those branches do not interfere in ways we can easily detect. Apply that to time travel, and a different style of protection appears. If you step into a time machine and go to what you experience as the past, your arrival lands you not in the single history that produced you, but in a parallel branch compatible with your presence. You can alter that branch freely. You can prevent disasters, change relationships, introduce new technologies. Nothing you do can create a paradox, because the branch you started from is not being edited. It continues separately, with a version of you who vanished into the machine and never returned. This does not keep causality tidy in the naive sense. It replaces one timeline with a vast web of them. But it avoids contradictions within any individual branch. From your perspective, the protection is more ruthless. You can never get what the fantasy of time travel to the past usually promises. You cannot go back and fix your own life. At best, you can create another copy of events in which someone like you has a different experience. To the people in your original branch, none of that matters. Their history is unchanged. In this way, the multiverse picture turns what looked like a power into a form of exile. The more dramatically you try to change the past, the further you move away from the particular chain of events that led to your existence. The universe protects its original narrative by letting you leave rather than letting you edit. There are other, more technical mechanisms as well. Quantum information theory teaches that information is preserved in unitary evolution. That is, the fundamental dynamics of closed quantum systems do not erase distinctions between states. When it looks as though information has been lost, as in the naive picture of matter falling into a black hole and disappearing, it is often a sign that we are using an incomplete description. Some speculative ideas, like the link between entanglement and spacetime geometry, sometimes called equals EPR, hint that the connectivity of spacetime and the patterns of quantum correlations are deeply intertwined. In certain toy models, signals that seem to cross a wormhole are really just ordinary quantum communication through entangled pairs, strictly respecting causality despite the geometry. If something like that holds in full generality, then the universe could allow structures that resemble shortcuts or loops at the level of geometry, while enforcing causal order at the level of information flow. You can draw a time-like path that appears to circle back. The actual channels along which influence travels remain forward only. Another boundary comes from energy conditions in quantum field theory. Even though small violations of classical energy bounds are possible, as in the Casimir setup, there are quantum inequalities that limit how much negative energy you can have and for how long in a given region. Those constraints make it hard to accumulate the kind of exotic energy densities that macroscopic wormholes or warp drives would require. Whenever you try to build up a dangerous configuration, the inequalities force compensating positive energy elsewhere or at other times, blunting the effect. Taken together, these patterns suggest that the universe uses redundancy. It does not rely on one single lock. Speed limits prevent simple faster-than-light signals. Light cones structure cause and effect. Energy conditions and quantum inequalities make exotic geometries incredibly hard to sustain. Chronology protection threatens to destabilize any serious attempt at a loop. Self-consistency locks any surviving loops into harmless scripts. Many worlds, if it describes reality, shunts the most dramatic interventions into branches where they do not disturb the past that made the intervener. None of these are friendly to the usual dream of a time traveler walking into a familiar room decades earlier and making a clean, decisive change. They are, in different ways, variations on the same theme. You are allowed to move in spacetime, even in extreme and strange ways, but you are not allowed to trivialize history. Seen in that light, the universe's protection is not aimed at us. It is simply what happens when local laws, quantum structure, and global geometry must all be satisfied at once. Time travel, as casual stories imagine it, would require that triangle to be broken. So far, every time we push on one corner, the other two push back. We can bend our paths. We can separate our now from someone else's. We can, in principle, ride gravity wells or high speeds to leap forward into futures we will never fully understand. What we cannot do is move through space-time as though consequence were optional. Consequence is a clean word on a page until it becomes a room you walk back into and no longer recognize. Up to this point, we have treated extreme travel as a question for equations and engines. How fast? How far? How much energy? But any path you carve through spacetime is also a path through a life. The universe can be indifferent to that. You cannot. Everyday time is held together by something small and fragile. The assumption that the people around you share roughly the same sequence of before and after. You wake up. Someone else wakes up. You both go to work. You both grow older by a similar amount between one meeting and the next. Even when your days are very different, your clocks stay close enough that you can age alongside one another. Extreme travel breaks that alignment first, long before it threatens anything in the deep structure of physics. Suppose a ship leaves Earth on a near light-speed journey. On board, the crew live through 10 years of work, conflict, boredom, repair, routine. They argue about small things. They mark anniversaries. They watch their own reflections change. Outside, decades or centuries pass. For the people who remain, the mission is a story that begins in their youth and ends in their old age, if it ends at all. For the crew, the same story takes up a single stretch of adulthood. When they return, if they survive to do so, they are not just travelers from far away. They are out of phase. Their slang is obsolete. Their cultural references fall flat. Iconic songs for them are nostalgic curiosities for everyone else, or forgotten entirely. The political struggles that shape their identities have long since resolved, curdled, or been replaced by others. They remember living debates that history has turned into a paragraph in a textbook, or erased. In Joe Haldeman's novel about relativistic soldiers, that is the core wound. The protagonist goes to war among the stars. Each deployment lasts months for him and spans decades or more on Earth. He returns again and again to a humanity that has shifted so far he no longer knows where he belongs. The book uses relativity as a metaphor for the dislocation of veterans in any era. As physics, it is also straightforward. Time dilation makes it literally possible to go too far ahead of your own generation to ever fully come back. Something similar sits in the middle of Interstellar. Cooper leaves his daughter behind to join a mission that might save the species. The price is not paid in equations. It is paid in a series of video messages. Each time he finds a way to watch them, his children have jumped forward years. Their faces and voices change while his barely does. Their sense of him slides from anger to resignation to a kind of distant acceptance. By the time he returns, the person he left is a very old woman. You do not need a black hole to feel a faint version of this. Long-term deployment, labor migration, incarceration. These already create mismatched timelines inside one planet with one gravitational field and low speeds. A parent leaves to work abroad for a decade. They send money, messages, small pieces of themselves through distance. When they come home, the children they thought they knew have formed identities in their absence. Relativity gives that same pattern a harder edge. It makes it physically possible to leave at 20 and come back at 30 to find your younger sibling older than you. Your city rebuilt multiple times, your culture transformed into something that treats your memories as archival footage. There is a limit to how much of that misalignment any person can carry. Psychologists who work with long-duration astronauts and polar researchers already see a version of the strain. Months in confined environments with a small group, cut off from the rhythms of ordinary social life, shape people in ways that do not always fit well when they come home. On the International Space Station, crews experience a steady cycle of sunrise and sunset every hour and a half. A constant hum of machinery, a thin shell between them and vacuum. Even with regular contact, they are, for a while, living in a different world. That different world leaves traces. Sleep cycles shift. Sense of danger and normality recalibrates. Some astronauts describe re-entry into gravity and crowd noise and unfiltered weather as a mild shock, both welcome and disorienting. Some speak of a overview effect, a change in how they hold humanity in mind after seeing the planet as a whole. These are subtle, mostly positive adjustments. Scale the mission up. Stretch it from months to years, then to longer than a single ordinary lifespan. Put the crew in a world where seasons and news and births and funerals happen far away and out of sync. Now you are asking small, social primates to tolerate forms of isolation they did not evolve for. Loneliness in that setting is not just being alone. It is being out of step with everyone you know, even as you talk to them. Messages will arrive with delays. Conversations cannot be immediate. A joke lands hours or days after the moment it was meant to soften. The crew form a small culture of their own. That culture has to absorb everything: grief, desire, boredom, conflict, meaning. In a generation ship, where the journey is so long that none of the people who arrive are the ones who left, the ethical questions deepen. Children are born into a metal environment they did not choose. Their home planet is an idea. Their sky is a hull. For them, extreme travel is not an adventure, but the default condition. They may decide that the mission that justified their parents' departure does not justify their own continued confinement. Here, the universe's costs are psychological and political rather than strictly physical. Relativity only sets the frame. You cannot both bring your descendants with you and keep some simple continuity with the world you departed. You must choose whom you are asking to pay the price of dislocation. Then, there are those who never leave. For a parent, a child, or a friend watching someone embark on extreme travel, time dilation is not an exotic effect. It is a kind of slow bereavement with a moving date. You lose a person in stages, first to training and preparation, then to delay and distance, finally to the gap they pass through while you age faster than they do. You might track the mission through news feeds, anniversaries, occasional messages that already feel like postcards from another age. You may take comfort in knowing that, from their perspective, not much time is passing. At the same time, your own life is unfolding at full speed. Health shifts. Family structures change. By the time they return, if they do, you may already be preparing for your own exit. Relationships can survive large differences in distance. They can survive many differences in belief and experience. Large differences in time are harder. A partnership that is built on shared memories and expectations can only stretch so far when one side has skipped over decades that the other has lived through. This is where stories about brave pioneer crews often grow thin. They show the departure, the mission, the heroic sacrifice. They rarely spend much time on the households that live with an absence that is not quite death, but not entirely presence either. Extreme travel makes that absence literal in a new way. There is also a social cost that does not land on individuals alone, but on how a civilization understands itself. If only a small elite can afford to participate in extreme travel, in near light-speed voyages, or in any future technology that exploits time dilation, then the gap between those who can and those who cannot becomes a temporal class divide. Some people gain the option to step over periods of crisis or instability, vanishing into long journeys and returning to whatever future emerges. Others must stay, experiencing every year of resource scarcity, climate stress, or political turmoil directly. It is not hard to picture how that would feel for those left behind, a sense that some have found a way to skip the hardest parts of shared history, a suspicion that decisions shaping everyone's future are being made by people who will not be around to live with the immediate consequences, because their personal clocks are already pointed elsewhere. Even without relativity, versions of this exist. Leaders and executives who can relocate easily, who can insulate themselves from certain forms of risk, already live in a different practical timeline from those who cannot. Extreme travel would harden that separation into physics. There is another angle. Any technology that allows high-speed travel or deep gravitational maneuvers will also have military and economic uses. The first entities to field such capabilities will be states or corporations, not artists and philosophers. Missions will be shaped by strategic goals: reconnaissance of distant systems, control over potential resources, symbolic demonstrations of power. The crew on such missions would carry not only their own hopes, but the weight of institutions. Their choices about when to report, what to transmit, whether to return, would have effects on political landscapes they barely recognize by the time any signal arrives. They might become, unwillingly, instruments of policy made on a world that no longer exists in the form that launched them. Back home, the very existence of extreme travel could warp expectations of the future. Why invest deeply in long-term repair if you quietly expect that, eventually, some fraction of the population will simply leave for new habitats made accessible by high-speed flight? Why tackle difficult reforms if you assume that those with the most agency can opt out of the timeline where failure hurts most? At the same time, there is a subtler, almost opposite danger, that we romanticize the people who leave and fail to see the slow, patient work of those who stay as equally extreme, in its own way. Holding a society together under stress, rebuilding institutions, adapting to a warming climate, caring for aging populations, these are forms of travel too, not through space, but through difficult sections of a shared history. The human cost of extreme travel is not only about suffering, it is also about what we choose to honor. Do we treat the person who slingshots around a black hole and returns to a different age as a hero simply because their path is geometrically dramatic? Or do we notice that surviving ordinary, constrained time with grace and responsibility can be just as hard? Underneath all of this sits a quieter tension, identity itself. You are held together not just by a brain and a name, but by a narrative you tell about where you have been and where you are going. That narrative is woven from memories that are anchored in shared events, school systems you pass through at the same time as others, cultural milestones you all absorb together, political moments you watched unfold collectively. When extreme travel severs those anchors, the continuity of self becomes less obvious. You can still say I, but the shared references that give that pronoun weight thin out. You become more like the man from Taured in the airport story. Someone who insists on a history that the surrounding world does not remember. That may be survivable for one person, with enough resilience and support. It becomes more complicated when many people begin to occupy such dislocated positions. A society of time-displaced individuals, each carrying their own partially incompatible histories, would need new ways of making sense of belonging. Laws would have to decide how to treat contracts, property, and responsibility when someone has been gone for what feels to them like a short trip and to everyone else like generations. Ethical frameworks would need to say what promises mean across such gaps. Personal faiths and philosophies would have to find language for lives stretched across unmatched timelines. Physics does not care about any of that. World lines are just curves. Proper time is just a parameter. But whenever we talk seriously about using the more extreme possibilities that relativity offers, we are obliged to lay those curves over actual human lives and look at the fit. Perhaps the deeper limit on extreme travel is not set by geometry or energy, but by how much mismatch a mind, a family, a culture can absorb before something important breaks. At some point, the question stops being how far we can go and turns into something quieter and harder. Who are we, if we decide to go anyway? The physics, on its own, is indifferent. It lays out a menu of paths and prices. High speeds that peel you away from the timeline of everyone you know. Gravity wells that fling you into the deep future and never let you back. Hypothetical shortcuts that demand forms of matter we have never seen, and that threaten to unpick causality if we mishandle them. What we do with those paths is not a physics problem, it is a character study. You can sketch 3 broad directions a species like ours might take if extreme travel remains on the table. One is to accept one-way journeys as part of what it means to be human. In that future, near light-speed ships leave regularly. Each launch is a kind of ritualized farewell. Crews know that when they come out of hibernation or decelerate into orbit around another star, the world that sent them will be separated from them by centuries of history. Colonies form that are, from the beginning, more like new branches of the tree than like remote outposts waiting to be resupplied. Over time, that tree sprouts in many places at once. Some branches keep a weak radio link, trading slow messages, histories, fragments of culture. Others go dark, whether through choice, accident, or the simple erosion of technology. Humanity becomes not one synchronized species, but a scattered family of cousins, each living in a slightly different slice of cosmic time. That path demands a certain temperament. You have to accept grief as a structural feature, not an accident. You have to normalize the idea that children will grow up planning departures that are also endings. You have to build ethics that treat someone who chooses a one-way relativistic voyage with the same moral seriousness as someone who chooses to stay and mend what is already here. Another path is more confrontational. Instead of accepting the universe's limits as hard edges, you treat them as puzzles to be bent. You pour resources into wormhole engineering, into warp concepts, into whatever new machinery our descendants invent, to lean even harder on the structure of space-time itself. You decide, as a civilization, that the risk of stirring up the subtler parts of physics is worth it. In that future, laboratories trying to stabilize microscopic wormholes grow into industrial facilities the size of cities. New kinds of accident appear in safety manuals. Border treaties include clauses about who may anchor tunnel mouths, where, and under what inspection regimes. Black budgets chase rumors of temporal weapons, even if the rumors are always one step ahead of what is actually possible. If chronology protection is real, that civilization will learn it the hard way. Projects will fail for reasons that look, at first, like engineering flaws, but over time, start to show a pattern. Certain geometries always destabilize. Certain feedback loops always explode. There will be debates about whether to keep pushing or to interpret the string of near misses as an answer. If chronology protection is not real in the strict sense, and some tame form of space-time manipulation becomes routine, the stakes climb again. You now have a technology stack where a design error or an act of malice can move ships, data, or radiation in ways that do not match ordinary expectations of distance and delay. The moral exam shifts from, should we try this at all, to, do we trust ourselves to keep this from becoming the last mistake we make? A third path is more modest on the surface and more radical underneath. You decide not to build machines that throw bodies across vast distances or deep into time. You focus instead on becoming very, very good at listening. That is the path we have already begun to walk without always calling it that. When the Hubble telescope stared at an apparently empty patch of sky and found thousands of galaxies, it was a kind of extreme travel by attention. When observatories sensed the ripples from two distant black holes merging, they overheard an event they will never visit. When radio astronomers assembled a planet-sized array to glimpse the shadow of a black hole in another galaxy, they turned Earth itself into a listening post. In a future where we lean into that choice, our main export to the cosmos is not our bodies, but our questions. We build better telescopes, more sensitive gravitational detectors, neutrino observatories, instruments that can read the chemical fingerprints of life in the atmospheres of faraway worlds. We map other people's neighborhoods without trying to plant flags in them. The cost of that path is different. It asks for patience and a kind of restraint that does not make for simple stories. There are no parades for the mission that did not launch. No iconic photograph of the first footprint in alien dust. What you get instead is a steadily sharpening picture of a universe that goes on without you, and the work of deciding how to live well in that knowledge. Of course, real civilizations rarely follow a single clean line. We may see all three tendencies at once. Some groups cradle their local world more tightly, choosing to stay. Others push for near-light speed expansion. Others sink resources into speculative space-time engineering. The question is not, which path will humanity take, as though there were a vote and a single outcome. It is, which of these impulses will we reward, regulate, or resist? One way to guess is to look at what we have celebrated so far. We built chemical rockets and sent them just far enough to place machines on the edge of interstellar space. Those machines carry gold-plated records, not weapons. We built orbital laboratories that circle our planet and use them to study fluid dynamics, plant growth, and the human body under microgravity, but also to look back at Earth, We turned radio dishes toward pulsars and quasars. We poured money into colliders that do not move anyone anywhere, except deeper into the structure of matter. All of that is a kind of answer. Another hint sits in how we respond to the small, real forms of time travel that already exist. We correct for relativistic drifts in satellite clocks because we want our maps and signals to line up, not because we enjoy the fact that different altitudes live at slightly different speeds. We do not yet send anyone on a mission whose main goal is to come back significantly younger than their peers. The extreme edges of what relativity allows are still, for us, mostly diagrams and thought experiments. That might change. As our tools improve, the temptation to use time dilation as a feature rather than a nuisance will grow. Perhaps some future deep space mission will be sold explicitly as a one-way ticket to a different century. Perhaps prospective crew members will record messages to descendants they will never meet, like letters to a future that might not remember their names. If the universe allows that, and everything we know suggests it does, the deeper question is whether we want to become the sort of species for whom that is normal. Do we train ourselves to treat human bonds as flexible enough to stretch across lost decades? Do we treat planets as stepping stones, valuable mainly as launch pads for the next leap? Do we pour our ingenuity into punching channels through space-time even when we can see the ethical risks outlined ahead of time? Or do we decide that the most interesting thing about being a conscious creature in a vast, indifferent universe is not how far we can fling ourselves, but how carefully we can inhabit the small region we actually touch? The story about the man from Taured lingers here for a reason. Real or not, he stands at the border of worlds, calm and bewildered, carrying documents that insist on a geography nobody around him recognizes. That is one image of extreme travel. The individual who has slipped between maps and pays the price in isolation. There is another image, less dramatic and harder to draw. A species that learns to live in its own slice of space-time with enough clarity that, when the doors to more extreme paths open, it does not rush through all of them at once. You and I will almost certainly never face that choice at the scale of light-speed voyages or engineered wormholes. The closest we may come is smaller. A decision to leave or stay, to skip ahead in our own lives or sit with a difficult present, to chase every possible movement or to pay more attention to where we already are. Still, the thought experiment matters. It frames a question that does not depend on rockets or exotic matter. If the universe quietly allows extreme travel, then the real test is not whether we can discover that allowance. It is what we are willing to sacrifice in order to use it. Maybe the measure of maturity for a civilization is not the first time it touches an event horizon or threads a wormhole, but the first time it says not yet, even when the mathematics says in principle. Yes. So if you picture a door in front of you tonight, one that would take you far into the future, or far across the universe, at the cost of everything familiar becoming unreachable, which part of you answers? The part that wants to see what comes next at any price? Or the part that thinks about who and what you would be leaving behind? If you feel like answering out loud, pick a path in the comments. Option A, spread outward with one-way journeys. Option B, keep trying to bend space-time itself. Option C, stay mostly here and learn to see the universe with sharper eyes. The question is simple. The reasons behind your choice are not.